That's the hard part, right? So I'm Dan Ransom. I'm an application engineer with General Electric Vernova. I'm out of Tacoma, as you heard Mike tell you, which is a little town just south of Seattle. Tacoma means big mountain in the native Indian language here. And that is what I am looking at out the window is Mount Rainier, 14,000 feet. I think second highest peak in North America. So good afternoon and welcome to this presentation on the essentials of renewable energy protection and monitoring. Here's what we'll investigate in our discussion. We'll start with the increase in renewables, the nature of IBR response, improving IBR operation during events, in particular with voltage ride-through and with frequency and power ride-through. And we'll also look at monitoring and protection assistance in maintaining power system stability. We've seen a big increase in renewables. Global renewable electricity generation increases to over 17,000 terawatts. That's 60 exajoules. An exajoule is 10 to the 18th joules for those of you who love metric. And that'll be in the next 5 years by 2030. And that's a growth of almost 90% from 2023, as shown here in the figure. By 2030, solar PV is the leading renewable electricity source, followed by wind, both surpassing hydropower, as you see here. There are many different types of systems that can be applied to the power network. The inverters systems can be wind, they can be photovoltaic, they can be battery energy storage systems. And these, along with gas turbines, hydrogen, electrolyzers, and storage, will be our modern energy fulfillment for our modern energy needs. These all feed the bulk power system represented by the transmission tower at the point of interconnection, POI. The nature of inverter-based resources response is a little bit quelled because IBRs use semiconductor switching devices that have control algorithms to protect against outputting large currents. These would destroy the semiconductor IGBT output devices. Typically, IBRs limit the fault current to 1.1 to 1.5 per unit of the inverter nominal current rating. IBRs do not produce the large fault currents that are typical of utility sources of synchronous generators. These generators can go instantaneously to 300% and more for a period sufficiently long to allow the conventional protective relays to act. Additionally, IBRs do not go through the synchronous machine subtransient, transient, and steady state phases of a fault, but rather the IBRs up until now have operated in an inconsistent manner. So it's difficult for an IBR system to distinguish the difference between a fault and a sudden load variation or an inrush current. This unpredictable action confounds the relay coordination scheme. So if we look back in time, let's start with IEEE Standard 1547, the standard for interconnecting distributed resources with electric power systems. It's evolved over the years since its introduction in 2003. The 2003 standard emphasized that DERs not interfere with distribution system normal operation. In addition, the other priorities of this original standard were worker safety and public safety. Tolerances for voltage and frequency excursions were very tight, and the standard mandated quick DER operation suspension. It mandated that DERs shall not actively regulate voltage. Well, that changed. Because of the increased adoption of DERs in the power grid, Amendment 1 came about in 2014. It relaxed some of the voltage and frequency targets. Now the DER may actively regulate voltage and may ride through abnormal voltage frequency and may provide frequency response, a frequency group response. This helped with grid support that is needed for adequate protection schemes, keeping the relays so that they have quantities on which to operate. So what the standard said is that IBRs must stay online depending on the severity of voltage and frequency excursions. Now, since 2014, a large influx of DERs, and this is mostly IBRs from wind and solar and battery energy storage systems, it required updating to the present 2018 edition. It specifies waiting for the cessation of operation depending upon the severity, how far it deviates in frequency and voltage. The types, as you can see here, are the following. There's category 1, which meets the bulk EPS reliability, applies to all DERs, including rotating machines. Where it gets longer is in category 2. We align with the NERC PRC-024-1. That's the generator frequency and voltage protective relay settings. And then category 3 is for low inertia systems, like a large concentration of IBRs. These can be supportive of the California Rule 14, or pardon me, the Hawaii Rule 14, the California Rule 21. As we can see, the times do not change much from 2003 to the 2018 category 1. However, the voltage and frequency ride-through requirements are now longer in the 2018 standard for voltage and frequency departures from nominal for category 2, and especially for category 3, as pointed out here. Protective relays can assist the IBR plant in monitoring and protecting outputs required by the 1547-2018. We'll discuss IEEE 2800-2 or -2022 next, as well as German and NERC grid codes like PRC-029-1 and PRC-024-3. You can place the relays at any of the red points of measurements as shown here on the slide, or a reference point of applicability. Usually the relay is at the default RPA. The relays can notify the IBR plant inverter controls of operation in the continuous, mandatory, and permissive operation regions via contact closures, sending it back from the relay at the point of measurement to the IBR controller, and thus the IBR controller gets immediate feedback. Relays send operational data back to the controller, and thus they can curtail the output of the IBR or allow it to trip or cause it to trip at the point of interconnect. So when a fault occurred, as I've mentioned, older IBRs suspended operation and had large variations in voltage, current, and frequency. And this caused incredible difficulty with conventional protection schemes because the relays didn't sense the faulted quantities for which they were looking. So recent standards and grid codes are improving the ability of IBRs to ride through load generation changes and faults. An example of the German grid code from the BEDEW, Bundesverband der Energie- und Wasserwirtschaft, or the German Association of Energy and Water Industries. It's the figure on the left. The figure shows the limit curves. We'll go back. It's the figure on the left. For type 2 IBRs, PEB and BESS, these have to remain connected, as we'll see here in PRC-29-1. During a voltage drop down to 0% UC for a duration of 150 milliseconds. Oh, that's the one on the right. And in the PRC-29-1, you can see that we also have requirements for times during which there's a voltage drop. The continuous operation range, which is at the top, is from 0.9 per unit to 1.05 per unit. The mandatory operating time depends on the severity of the voltage fluctuation. This is the LVRT zone, low voltage ride-through. So from 0.7 to 0.9 per unit, you've got to be on 6 seconds. 0.5 to 0.7, you've got to be on mandatory for 3 seconds. And it gets smaller as you get towards the less and less voltage in the system. At the bottom is the permissive operation region at less than 0.1 per unit. Here, the IBR plant may continue to exchange current with the transmission system, or it may operate in current blocking mode. It can shut down, but it's got to be on at least, in this case, 320 milliseconds. That's forever in relay time, so that will help the protection systems operate. The goal here is to avoid service interruption and poor power quality by maintaining the power system synchronous inertia and supporting protection schemes. IEEE Standard 2800-2022 expands on the previous work of 1547 and the grid codes and some of the NERC early codes. It emphasizes the areas for improvement and standardization in IBR plant operation. The focus is on grid stability and consistent responses from IBR controllers. The standard establishes minimum technical requirements for the interconnection and performance of the IBR plants connected to the transmission system. The standard includes specifications for voltage and frequency ride-through, active power control, reactive power control, and dynamic active power support under abnormal voltage and frequency conditions. IEEE 2800-2 or -2022 covers IBRs with auxiliary equipment and without auxiliary equipment. It includes the NERC equivalents of PRC-024-3 and PRC-029-1. The updated PRC-024-3 is IBRs with auxiliary equipment, including synchronous generation and most newer wind plants. And NERC PRC-029-1 has similar voltage and frequency requirements to 2800 for IBRs without auxiliary equipment. So here's a look at the voltage ride-through requirements from IEEE 2800. The IBR plant must meet specific voltage ride-through requirements. And here you can see those as the continuous operation range. That's at the top from 0.9 per unit. In the case of 2800 to 1.1 per unit. In 29-1, it's 1.05 per unit. The IBR must provide pre-disturbance active power or minimum available active power while adhering to the maximum current limit, Imax. After 1 second during the overvoltage period, or the overvoltage levels from 1.1 to 1.2 per unit, in that period, the IBR may trip or continue to ride through. Tripping or current blocking prevents IBR damage. As we go lower in voltage into the mandatory operation region from 0.1 to 0.9 per unit, the low voltage ride-through region, the IBR must inject current to the maximum limit Imax to support grid stability. After the specified time at a voltage level, the IBR may trip or continue to operate. The standard requires automatic voltage control during ride-through while adjusting fault current fundamental frequency, and I'll show that in a moment, depending on the voltage deviation from normal. And as you get down to a very small voltage, a big load or a heavy fault, that's the permissive operation range. Here it extends from 0.0 per unit to 0.1 per unit. In this area, the IBR can exchange current to the maximum current limit or operate in a current blocking mode, but it has to wait at least 0.16 seconds. That's 160 milliseconds as shown on the left for auxiliary equipment IBRs, and longer, 320 milliseconds as shown on the right for IBRs without auxiliary equipment. Those would be photovoltaic and battery energy storage systems. So how can a protective relay help the IBR plant get this right? Well, here's how. We've got a timed undervoltage 27T element that follows the V versus T curves. If you were to do this in a conventional relay, you would need lots of undervoltage elements. So we've made one that'll track on a graphical basis. It's a timed and count qualified phase undervoltage 27T element, and it keeps the IBR operating to prevent grid collapse. It's time dependent. It has 10 configurable points. The relay monitors grid support for brief voltage drops and responds for voltage drops that enter the operation region of the configurable curve as shown here. If the voltage drop exceeds the timed undervoltage element issues a notification to the plant controller. And here you see the graph alone without the standard behind it. Here's the German BDEW grid code, and here are the 27T curve coefficients for the German BDEW grid code. And here's the relay graph without the code behind it. Also in 2800-2022, there is a clause that states the IBR plant may trip if there are cumulative effects of successive voltage deviations, undervoltages and overvoltage. Particularly the undervoltage area is what's challenging for the IBR plant. So the 27T element includes a counter-based protection that counts the number of transient voltage drops and trips according to the the provided threshold for the given time window. If the number of transient voltage drops exceed the threshold within the overall element time, then the relay issues a trip or IBR plant curtailment signal. If the voltage drops are greater than 50%, as you can see here, in 10 seconds, you can have 4 and then you're allowed to trip. If the voltage drops are more severe, under 50% of VNOM, then after 2, the 27T element operates and signals the controller. In recent standards and grid codes, the DER unit feeding into the transmission system must support the power system voltage upon a network failure. And the purpose of this is to keep stability in the system. The 27Q element shown here does that. If a voltage drops and an inductive reactive power flow in the direction towards the generating unit, that's reverse, is detected, then the network connection point needs to have something happen there to take off the generation system, to disconnect it, be CB1 or CB2. When the element's set to reverse under normal conditions, the power flow can be either way, but what's important is that the VARs are flowing into the IBR system. So protection will trip if the reverse reactive power measurement is positive in the reverse direction and exceeds the programmed pickup VARs level and direction. There's a restoration function that'll keep it going and get it sync checked as it comes back online automatically. Sometimes the IBR must accept VARs, take in VARs, to reduce an overvoltage condition on the system. So you can set the element to also monitor that condition. And now we come to frequency. We've been talking mostly about voltage ride-through. Frequency ride-through is also very important in how it affects the power provided by the IBR plant. The standards say that the plant shall ride through a disturbance and maintain synchronism with the connected grid according to frequency. So the frequency response is divided into two parts, the primary frequency response and the fast frequency response. The standard allows for adjustments to remain within volts per hertz limits, including the IBR units, transformers, and supplemental devices. For NERC PRC-024-3, the required responses are based on region, Eastern, Western, ERCOT, Quebec, etc., and your region. So what we need to get a relay to signal the IBR plant controller is fast frequency response. The relays typically in the past used a whole cycle to measure frequency, and that was slower. So now we've got relays measuring half cycle crossings of the voltage waveform as seen here. So in this case then, as you can see in the slide, there are 5 to develop the count and 3 to reset the count. And in this way, we can get the times in half. And that's very, very important when you're trying to get grid stability going. Time is your friend. The 2800-2022 and the PRC-029-1 standards state that the IBR plant shall ride through a frequency disturbance and maintain synchronism, and this is the frequency chart. The continuous operation around nominal is at plus and minus 2%. The overfrequency ride-through is plus 3% for 299 seconds, and the underfrequency ride-through is minus 5%. You can go a little bit more for 299 seconds. The transmission system operator may specify the region after 299 as mandatory. The minimum mandatory is 299. Otherwise, the IBR plant after that time may continue to ride through, or it may trip. The plant adjusts active power as required during and after a frequency excursion defined by the deadbands with fast underfrequency elements, 81U, that I just discussed. This helps the grid frequency recover and be stable. The IBR injects power based on the departure from the frequency, and that's in a frequency deadband dB under frequency, dB UF, and dB OF, dB over frequency. And these are at the droop rates of KUF and KOF for under frequency and over frequency deviations, respectively. Here's an under frequency case. The IBR maintains the power output, P pre, while the system frequency is dropping. At the end of the under frequency deadband, the IBR increases power to the new operating point, and this furthers stability in the grid. Along with primary frequency response, there is fast frequency response. This is during the arresting phase of the frequency excursion. FFR is similar to PFR, but it's faster, and it has a droop percentage to 1%, provide 100% change to power for a 1% change in frequency. FFR is active only to the applicable frequency nadir point, to where the arrow is pointing here in the slide. The FFR step response time capability has to be within 1 second. Triggers for FFR are specified based on frequency deviation or the rate of change of frequency DFDT and active power targets for under frequency, as you can see in the math equations here. The IBR plant will sustain FFR for as long as the IBR plant energy resource is available or until supplanted by primary, secondary, and tertiary frequencies. So what this looks like in a relay is that the FFR and PFR have a relationship. Here are the 81U elements. Here are the 81U elements in the relay are helpful for determining FFR1, FFR2, and FFR3. And the rate of change of frequency, Raukoff1, is the DFDT of the D trigger for FFR4. The protective relays have to keep their frequency response and primary frequency response, both the fast and the primary. These are independent and they complement each other, as seen here in the formula on the bottom of the slide. The power equals the minimum of the available power, or P pre plus the PFRs. Well, what we've seen here in the presentation is that inverter-based resources are contributing more to the overall generation mix of the bulk power system. Recent grid codes and standards like 2018 or 1547 2018 2800-2022 PRC-029-1 and PRC-024-3 have a mandatory operation and ride-through for both voltage and frequency from the excursions from nominal. I've shown you a timed count qualified phase undervoltage element that exists at the point of metering, the reference point of applicability, and it signals the IBR plant to perform mandatory operation so that we can prevent grid collapse. The standards, national grid codes, and regulations require also not only voltage protection, but frequency ride-through protection as well. And you can see those in the 81O and U elements and the 81R Raukoff elements. Now it's time for your questions and comments.
Thanks, Dan. Going to see how many questions we have here in just a minute. Hopefully my audio hopefully is back.
You're back.
And, okay, good deal. Sorry about that earlier. And we also would like to hear just before we go to our questions, we wanted to just invite Andrew Benjamin from our compliance monitoring group to say a couple of words about the recent activity on the approval of standard PRC-029-1. So Andrew, let me go ahead and jump on here if you can.
Sure, absolutely. Can you hear me okay, Mike?
We can hear you.
Great. Good afternoon, everyone. Thanks for your attention. And Daniel, thank you for such a great presentation. There was a lot of really great and important information. This is a a topic, as I'm sure you're all aware, that is of growing importance around the region and around the ERO enterprise. My name is Andrew Benjamin. As Mike mentioned, I'm Senior Technical Auditor with Reliability First. And I just wanted to cap off Daniel's excellent presentation with just a quick look at some of the milestones for PRC-024 and PRC-029 and where we're all headed together. So as Daniel mentioned, the growth of the inverter-based resource industry and its impact on the bulk power system presents both opportunities and challenges to all of us within the ERO enterprise. The proportion of IBR resources within the ERO's generation mix is growing rapidly, as Dan mentioned, due to the technological and economic advancements. And with these resources, when they were first introduced, they were utilized within tight tolerances, and sudden disconnection from the bulk power system was not of significant reliability concern due to the limited implementation, as Daniel mentioned. But as these IBR facilities become widespread across the ERO, they will have an important and growing role in maintaining system reliability and supporting voltage and frequency across the bulk power system. So with that being said, the intent of PRC-024-4 and PRC-029-1, both of which received FERC approval just this past July, is to ensure that IBRs connected to the bulk power system have sufficient ride-through capability to stay connected during defined frequency and voltage excursions. Because maintaining their output within the no-trip zones of these standards will help IBRs to support the bulk power system reliability during the kinds of events where available generation capacity is especially important. These standards should help IBRs behave more like traditional synchronous generators and individually help contribute to the resiliency, stability, and overall reliability of our bulk power system. Both of these standards are currently scheduled to become effective in October of 2026. If you would like some more information, the implementation plans for these two standards, as well as their NERC project 2020-02, can all be referenced on NERC's website for those specific details of the phased-in compliance dates. Overall, the modifications to PRC-024 with revision 4 and the creation of PRC-029-1 should result in a stronger bulk power system that is more responsive and more reliable during sudden changes in system conditions. They will allow generation resources of all types and sizes to contribute to our collective stability and resiliency. So I want to thank you again for your attention and your participation. Hopefully we have some really great questions coming out of Daniel's presentation. Again, a lot of excellent information from that. And here at RF, we look forward to working with all of our registered entities on making these improvements and taking these steps together. Thank you.
Okay, thank you. Dan, we do have some questions that have popped up in the chat.
Good. That's great.
The first one is regarding the frequency response. Does it matter that there is no spinning mass inertia? A traditional synchronous machine also has frequency response, and it may not be as fast, but maybe it halts frequency drop better since it's a spinning machine. Thoughts? And if you need me to reread that, I can.
Sure. Yeah, the IBR, one of the beauties of it is that it's fast. So if we can corral the response into the area we want it, this is actually a benefit for the bulk power system, because as the questioner mentioned, rotating machines are slow to get back on frequency. So the IBR plant is actually a plus. So it's a benefit in this case, in that it can respond quickly and put that power and frequency to the point it needs for stability.
Okay, thank you, Dan. The next one we have, they're asking, is the 27T element based on single phase or three-phase voltages?
Configured to what you have to measure. I'm just going to pull up the slide here, but my CL slides, there we go. Now it's working. So let's look at the PRC-29. And the 2800 and the 29 are pretty close. They only vary in the overvoltage region, but mostly this element works in the undervoltage region. So yeah, it'll help the IBR plant maintain limits that it needs to see. And it's measuring at the point of applicability, not way upstream where the controller is. Was there a second part to that question?
No. And then the next question that we have is regarding the relaying. What are your thoughts on short circuit current impacting zone distance relaying? And do you think too many inverter-based resources on the system will impact coordination, especially for distance relaying?
Yeah, distance relaying is another topic I didn't discuss here, but it's a definite problem for determining what the distance is. The ride-throughs will help because V equals E over I. When E is constant and I is very large, of course, the distance zone comes smaller. But if we can keep that voltage up, the distance element has a better possibility of determining the right distance. So if it's in zone or out of zone.
Okay. Thank you, Dan, for that. Let me just check real quick to see if we have any additional questions. Here's one more. It is how is the inverter setting and the relay setting, how are those coordinated?
Well, that's a good question. And what some people do, if I can point here, let's see if I can point. Okay. So, for example, do you set the relay at the edge of the cliff, or do you set it back here to warn the IBR controller, hey, I've been 2 seconds now in the 0.5 to 0.7 range. Should you think about starting to do something? So that's kind of like two philosophies of protection. Do you set at the fence and then say, Katie, bar the door, or do you set the fence back from the edge of the cliff and then allow some corrective action before you get to the time? So it's a philosophical operation of your protection system. Here or here.
All right.
Here or here. This gives you a little bit of time to do something.
All right. Thank you, Dan. Do you see anything else you want to add to that? I think that's all the questions I see currently.
I'd just like to thank the attendees for their attention to the presentation and for their time.
Yeah, and we want to thank you, Dan. And what really impressed me about your presentation was how proactive this is. This is not just a presentation about how to comply with the NERC standards. This gives great guidance and information about the IEEE standards on how to apply this to any inverter-based resource. So thank you for sharing with us. We may have some additional materials that we can post on our YouTube site if anyone is interested in that. So thank you so much, Dan.
It was my pleasure. Thank you for inviting me, and I'm looking forward to our next talk.
Appreciate you.